Okay, so we would like to find a potential for the conservative vector field given by this formula. And here the idea is similar to two dimensions. So we begin with a first guess for the potential by taking the antiderivative of the first component with respect to x. I actually remember that if phi is a potential, then this is supposed to be phi sub x, this is supposed to be phi sub y, this is supposed to be phi sub z. So it makes perfect sense to take the indefinite integral of 2xy plus z with respect to x. And if we do so, we're going to find x squared y plus xz or zx. You can write it any way you'd like. And now here's the interesting thing, which is very similar to what we had in two dimensions. We cannot really say that all we're adding here is a constant, right? Because since partial differentiation is implied here, we can have any expressions of y, any expression of y and z, and when we take the partial derivative with respect to x, that would have vanished. So instead of a constant, we put g of y comma z, and we should try to pin down the function g, y, z, so that the derivative of all this expression, meaning this one, with respect to y is the second one, and with respect to z, it's the third one. So in other words, the requirement here is that the derivative with respect to y of x squared y plus xz plus g of yz should be equal to x squared plus 3y squared z. And the partial derivative with respect to z of the same thing, meaning the first guess for the potential, should be equal to the third component, which is y cubed plus x plus 1. And this should be sufficient to help us pin down the function g. Now, what is interesting here is that once we take these partial derivatives on the left, what we get is x squared plus g sub y equals x squared plus 3y squared z, and x plus g sub z is equal to y cubed plus x plus 1. And we have a cancellation here, and what cancels is exactly all the x's. And that is crucial, because we're looking for an expression of gy and gz. I'm sorry, we're looking for an expression of y and z, that would be the function g. And eventually what we get is the following system. G sub y is 3y squared z, and g sub z is equal to y cubed plus 1. Now, guess what this is? This is precisely the type of problem that we got when we solved when we found a potential for a vector field in two dimensions. In other words, what we have in our hands here is an inductive process. And that tells us that, for example, if you were doing the same thing in 4 dimensions, then after your first step, you would get a problem in 3 dimensions. And after one more step, you would get a problem in 2 dimensions that we solved for 2 dimensions. We saw how to solve it. And eventually you can backtrack and you will have the solution to the initial problem. So in other words, what we need to do here is one more argument of the same type. So I will say that g of yz is going to be the integral of 3y squared z dy. And this, of course, is y cubed z plus a function of z. Okay, again, since g is a function of y and z, and it has been partially differentiated with respect to y to give us this, any expression of z would have disappeared by that partial differentiation. So finally, we need to pin down h, and we do that by requiring that the partial derivative of what we just found with respect to z is equal to that, which is exactly what we wanted to begin with. Okay, so we get y cubed plus now regular derivative, ordinary derivative of h with respect to z is equal to h cubed plus 1. Again, it's crucial that all the y's disappear. We get h prime of z is equal to 1, which means that h of z is equal to z. You could add a constant here, but that's irrelevant. Remember, we just wanted to find one potential, not all of them. So now we start backtracking. So we will have that gyz is going to be y cubed z plus z. So that gives us g of yz, and eventually phi of xyz is going to be our initial guess plus the g of yz that we found. So what was it? It was x squared y plus xz. So x squared y plus xz plus y cubed z plus z. And that's the potential that we were looking for. Thanks for watching.